Have you ever picked up a rock and just wondered where it's been? What if I told you that some rocks have their entire life story written right inside them? A story written in minerals. Today, we're going to learn how to read it. So, that's the big question, isn't it? How can a chunk of stone tell us its autobiography? I mean, how can it possibly reveal that it's been on this incredible journey? Maybe even to the bottom of a subduction zone, miles deep inside the earth. It sounds kind of wild, but it's not magic. It's just geology. And here's the secret to the whole thing. Metamorphism isn't random. Rocks don't just change for the fun of it. Nope. They transform in very specific, very predictable ways, all based on the conditions they're put through. That predictability, well, that's our key to everything. All right, so let's get into it. Section 1. Decoding the mineral clues. We're about to learn the language that rocks use to tell us their secrets. The key idea here is something called a metamorphic facies. Now, this isn't just one mineral. Think of it as a whole team of minerals, a specific group that always, and I mean always, forms together, but only within a very specific window of pressure and temperature. They're a package deal.
So how does this actually work? Well, it all comes down to stability. At any given pressure and temperature, some minerals are perfectly happy and stable, while others just can't exist. So if conditions change, let's say a rock gets buried deeper and heats up, the old minerals literally break down and their atoms rearrange themselves to form a brand new set of minerals that are stable in that new environment. They're basically acting like tiny built-in thermometers and pressure gauges that lock in the conditions they experience.
Okay, so let's build on that. You can imagine this whole process like climbing a ladder. Each rung you climb represents more heat and more pressure, and on each rung you find a totally different group of minerals, a different metamorphic facies. So down at the bottom of the ladder, we've got the Greenschist facies. And you guessed it, it's named for its distinct green minerals, like chlorite and actinolite. When you see that green color, it's a dead giveaway for relatively low pressure and temperature. These are the kinds of conditions you'd find in the shallow crust, when mountains are just starting to form. We climb up a rung, and now we're in the amphibolite facies. Things are heating up. With more pressure and more heat, those green minerals aren't stable anymore. They get replaced by darker, tougher minerals like amphibol. The whole look of the rock changes, telling us it's been through something a lot more intense. Now we're at the top of the common sequence, the granulite facies. This means really high temperatures, way down deep in the crust. Here, even tough minerals like amphibol can't take the heat. They break down, and we start seeing things like pyroxene and garnet. This facies also tells us it was a very dry environment. Any water in the rock would have been cooked right out. Now, you've probably heard people talk about low-grade or high-grade metamorphism. And that's okay, but there's a reason geologists are so specific about using the word facies. Grade is kind of vague, right? It just tells you if things were intense or not. But facies, that's specific. It nails down the exact pressure and temperature window, which lets us point directly to a specific tectonic setting. It's way more powerful. And that brings us to the really cool part, tectonic fingerprints. Some of these facies are so unique, they're like a geological fingerprint left at a crime scene. They point to one, and only one, kind of dramatic event. Okay, check this out, the blueschist facies. Look at those conditions, high pressure but low temperature. Now wait a second, how is that even possible? Usually, when you bury a rock deep enough to create high pressure, the temperature goes way up. Well, there's only one place on Earth where this happens, a subduction zone. That's where a cold, dense oceanic plate gets shoved down into the mantle so fast that it doesn't have time to heat up. This unique origin makes blueschist incredibly rare and an absolute smoking gun for subduction. But what happens if you go even deeper down that subduction zone? Well, then you get eclogite. This facies signals extremely high pressures, and it's defined by this beautiful, unmistakable mineral combo, a type of red garnet living right next to a bright green pyroxene called amphibole. When you find those two together, you know that rock has been on one heck of a journey.
So the bottom line is this. Finding an eclogite is like getting a postcard from the deep earth. It tells us, with zero doubt, that this rock was dragged way, way down into a subduction zone and then somehow, against all odds, made its way back to the surface for us to find. It's a true geological survivor.
All right, let's tie this all together. In our last section here, let's look at what these rocks are really telling us. I think a simple analogy will make it all click into place.
Just think about cooking. You can take the exact same ingredients, let's say some meat and veggies, and cook them in your oven.
You get one result. Now take those same ingredients and throw them in a pressure cooker. You get a completely different dish, right? The ingredients didn't change, but the conditions, especially that high pressure, did. Metamorphic facies are just like that. They're telling us about the cooking conditions, not just the ingredients.
And this is the fundamental truth, the one thing you have to remember. Minerals don't lie. A mineral can only exist in its specific little comfort zone of pressure and temperature. So if you find that mineral in a rock, you know for an absolute fact that the rock must have experienced those exact conditions. It's a physical record.
So let's just do a quick recap. Greenschist tells you low pressure and temp. Amphibolite means things are getting hotter, medium pressure and temp. Granulite tells you it got really hot. And then you have our special fingerprints, blueschist, the unmistakable sign of subduction, and eclogite, which tells you that rock went to extreme depths in that subduction zone.
When you boil it all down, it comes to this one powerful idea. Metamorphic facies are just nature's way of putting a label on a rock. A label that says, here's where I've been, here are the pressures and temperatures I survived. It's a life story just waiting for us to learn the language. So next time you pick up a metamorphic rock, what story do you think it's going to tell you?